Hey, my name is Ben. Today I'm going to explain regression using a simple algorithm called linear regression. Make sure to like and subscribe if the video was helpful. So, let's plot a data set about housing prices, where on the y-axis we have the selling prices increasing from the bottom to the top, and on the x-axis we have the square meters of the house increasing from left to right. Now we want to predict the price at which we can sell a house given its square meters. A simple way to do this is by approximating the data given a linear function which is represented by the orange line. Now we can predict the price for any house given its square meters. You are probably asking yourself, how do we get this linear function? This is actually quite easy and only requires a little bit of math. Since our model represents the data by a linear function, we will actually predict the prices with a small error for each individual data point. These error terms are called error residuals and are represented by the red lines on the graph. Since we want to represent the data as accurately as possible, we want to minimize the sum of these error residuals. To measure each individual error residual, we can use a function called the squared error. So the error residual, represented by the letter epsilon in the formula, is equal to the squared difference between the ground truth y, which is the actual price of the house, and the prediction of the linear model, vt times x. Note that this is in matrix formulation. You can check out the tutorials on mintube.net to get a better understanding about matrix notation, since this will be extensively used in machine learning. So again, we want to find the weight vector v representing the linear function that minimizes the total squared error. Note that now we have a big X where we previously had a small x. The big X means that it is every single data point in the data set. So this can also be reformulated as the sum over the individual error terms. Note that the sum goes from 1 to n, where n denotes the number of data points in the data set. Usually, one would use the matrix formulation because then we can use powerful GPUs to calculate those solutions. To get the minimum of a function, you should derive it, set its derivative to 0, and then solve the equation. We will also follow these steps, but since they're not that interesting to watch, you can check out the step-by-step solution on my website. It is a good exercise to try to do the reformulation yourself and also try to find out the weight vector v. If you can't come up with the solution, the website got you covered. So let's get back to the video. We reformulate the target objective to get this term. Then we're going to derive it with respect to the weights v and set its derivative to 0. Now we got a weight vector v. This is also quite easy to implement, but keep in mind that the inverse of the matrix actually costs a lot of time. And therefore, sometimes it might be easier to just use a gradient method if your data set is very, very large. So I created this little notebook to get a little bit more of a hands-on feeling on linear regression. It should be quite straightforward to understand. And I'm also going to upload it to GitHub so you can just download it and run it for yourself. So the first thing I'm going to do is I'm going to import all the different frameworks that I'm going to use. I'm going to use NumPy for efficient matrix multiplication and sklearn since it provides nice data sets. So first we can generate some data. This is also the data that I showed you previously in the video, so it's already explained. Now what we're going to do is we're going to calculate a model. I told you that the linear function is v transposed times x, which is true, but we actually did one step before, which is adding the bias into the weight vector. So usually a linear function looks like this. So it's just a times x plus b, where b is equal to v0, which is biased, and v is equal to the slope a. What we did is we augmented the data with a 1 so that we can simply integrate v0 into the weight vector. So like this. When you will calculate the matrix multiplication, you will multiply v with x plus v0 times 1. So we just create the ones with as the same length as x. Then we augment x with the ones, and we calculate v given the function that I showed before. So we can just run that. You can see we augmented, we have 500 data points with a single value, and also 500 ones. Then we augmented it, so each data point now has 2 features, which is the one and the actual data point feature. And our weight vector will then have 2 values, which is here the biased, which is multiplied with the 1, and the slope v, which is multiplied with x. We can also plot some data points. So this is what a prediction looks like of a simple of a single data point, and we can also now do this for every possible square meter in our data set. So I'm just going to go ahead and run it. It's also quite important that we augment our predictions as well, otherwise the shape will not match. So this is a model that we predicted, which is simply the blue line. If you have any questions so far, just leave them in the comments and I'm going to try to answer them all. For polynomial regression, we go a little bit further. So we don't only augment the data set with a simple one, but we augment it with polynomial features. So it's actually quite easy to understand. So this was our data set before, and now we augment it with x to the power of 0, x to the power of 1, and x to the power of 2. You can also go further, but what we want to do is we want to match a squared function. So here you can see the linear model fail because it just plots, because it consists of a linear line for a squared function. So the error residuals will actually be quite large here, and it will be a very bad model for data. What we want to do now is, as said, we want to use the polynomial feature augmentation to get a better fit. So we can just go ahead and run it, and you see that now we have actually a squared function as a model, which is actually quite nice and fits the data very well. One more thing to mention is that also here we have to augment our new data points that we have not seen in the data set so that the shapes match again. Yes, actually it is still a linear function because we did not really change the formulation. So it's still f of x of v times x. So f of x equals v times x. Therefore it is still linear in terms of data points and the weight vector v, but we augmented each data point polynomially. Therefore it looks like a polynomial curve. So I think it should be quite clear. As said, if you have any questions, just leave them in the comment section. So thanks for watching. If you have any wish for a specific video, just leave it down in the comment section and I'll get it done, hopefully. So, bye!